In this video, I would like to show you that the online platform Tree of Knowledge can enable social science researchers to create an exact social science. To understand what is meant by exact science, let's look at physics. The models in physics, the physics equations, are so rigorously proven that we often call them laws of nature. In other words, we have absolute trust in their correctness. These physics models are super versatile. The laws of mechanics, for example, allow us to correctly model absolutely any mechanical system. And these models make 100% accurate predictions. This ability to make 100% accurate predictions about any physical system is incredibly powerful. Only through physics' exact predictions were engineers able to develop and design the modern technology we rely on every day. But how does it work? What is special about physics' approach to modeling that make its models so incredibly powerful? Concerning how rigorously proven the models are, in physics, the models describe a fundamental generic object, such as a solid. We can now, say, make a 3D model of a motor and accurately simulate the movement of every solid component in this motor using the generic laws of motion for solids. The same laws of motion can be used to model the solid components of any mechanical system. The remarkable thing is that these simulations have been shown to be 100% accurate over and over again in scenario after scenario. Seeing that these fundamental, generic laws for solids work correctly in all these different scenarios gives us this incredibly strong confidence in their general correctness. So, this is where the confidence in the physics models comes from. Concerning versatility. As mentioned earlier, we can use these fundamental generic rules to accurately model any mechanical system, including systems we have never seen before. This can be especially useful for, say, designing new products. Concerning accuracy. The physics models are microscopic models, which means that we model each and every tiny component of a system. Most social science models, on the other hand, are macroscopic models. They don't consider all the individual components. Instead, they only model the shape of a single macroscopic variable, such as the engine's power. Advantages of the microscopic models are that they are inspectable. They allow you to learn about and understand the interplay of its individual components, and that a detailed model of all the system components can give us a greater accuracy. This is where the accuracy comes from. We can see that the physics approach is incredibly powerful and successful. Seeing how amazingly successful and powerful the physics approach is, this begs the question: can we copy this approach with the generic fundamental model and apply it to social sciences? Well, people have tried. The problem is that social systems are much more complex, interconnected, and uncertain than physical systems. Here are some quotes from famous physicists, all saying that social systems are much harder to model. It was quite easy for Newton to come up with the correct rules of motion for solids. He was one of the first people to try, and got it right pretty much on his first try. Modeling humans, on the other hand, is much harder. Whenever we've tried to come up with a set of rules for human behaviour, they always turned out to make very wrong predictions. Time and time again. It just isn't that easy that we can randomly come up with or guess the correct behaviour rules for humans. So, applying the physics approach to human systems has so far led to a terrible accuracy. Let's look at one of these wrong model predictions more exactly. We see it to be wrong because some system variable, say the number of customers, was different in reality than it was in the simulation. Here, we can see that the prediction in blue is really very far off from reality, giving us an accuracy of only 14%. Now, these terrible predictions of classical mathematical modeling have led to another approach: statistical modeling, i.e., fitting a curve to the real-world values, the number of customers. This approach of fitting a curve to the real values gives us a fantastic accuracy. In this example, 92%. In general, these statistics or machine learning models give us very accurate predictions for the one system variable they are fitted to. It might not be the 100% accuracy of the physics models, but they will be at least 90% accurate. Unfortunately, modelling the shape of only a single of the system's variables doesn't teach us much about the system's components and their interactions. And we lose the versatility. We can now only model systems for which we have data. Most critically, however, is that these models are always evaluated on only a single dataset, which doesn't give us great confidence in their correctness at all. The replication crisis has shown us that many of these models won't stand the test of time. So, to summarise all that we have discussed so far, when we apply the physics approach to social sciences, we get proven and versatile models that, however, aren't accurate at all. The statistics and machine learning models do give us a good accuracy of over 90%, but instead are neither proven nor versatile. The ideal for us would be to have a model that has it all, that is proven, versatile and accurate, as such a model would allow us to have exact social sciences. I would like to present to you a new approach to mathematical modelling that combines the best aspects of the modelling approaches we have discussed so far. By combining the best aspects, we can achieve something that is proven, versatile, and over 90% accurate, and gives us 100% accurate probability distributions. I believe that this new approach will allow social scientists to create a model that can safely be called an exact science. This new approach has been implemented in the statistics software tree of knowledge. So, how does this new approach work? Well, it is inspired amongst others by engineering software. With engineering software, you can select different objects that you want to model. Specify their properties such as size and position, and press play to simulate how this system unfolds. To make these accurate simulations, the engineering software simply applies the fundamental behaviour rules for solid objects to all of the objects in the system. Tree of knowledge works in the same way. To model a system, you simply specify the agents that are in the system, as well as their properties, such as age, gender, nationality, and whom they are married to. Once you've specified the system, you can press play and the program will simulate this system. To simulate this system, Tree of Knowledge uses fundamental behaviour rules of humans and of countries. This is what one of the simulations might look like. For every time step, we calculate all of the person's attributes, such as age, gender, etc. The simulations usually include much more than just these 4 attributes. In the example here, a time step size of 1 year was chosen, but we can choose any time step size. To model something like emotional reactions, it might make more sense to look at seconds instead of years. As mentioned before, the simulation is done using fundamental behaviour rules of humans. The rule for calculating the age, for example, looks like this. It says that the age increases by 1 every year. Here, the rule for calculating someone's happiness looks like this. It depends on the person's hunger, the happiness of their spouse, and their country's average happiness. As we don't exactly know how strongly these factors influence someone's happiness, this rule here is a statistical model with unknown parameters. We can train these unknown parameters in 2 different ways. If we have a dataset in which happiness is directly observed, such as a study on happiness, then we can use Bayesian inference to directly fit this function to the data, i.e., to learn for which parameter values the rule is the most accurate. Unfortunately, there are only a few studies on happiness. There is, however, a massive amount of data sets out there in which happiness plays an indirect role. So if we have such a data set in which happiness plays an indirect role, say a data set on people's purchasing decisions, then we train the happiness rule using simulation-based inference. For this, we make a simulation model of the initial state before people have made their decisions. We do this by dragging and dropping all the agents into the system and specifying their details. Now, if we run this simulation, we would like it to unfold in the exact same way as reality had unfolded. So now we can learn the same happiness parameters we saw before. The software does this by trying out different parameter values and learning for which values we get the simulation that most accurately mimics reality. These are the two ways the software can learn unknown parameters of a behaviour rule. In general, the users of Tree of Knowledge are mainly interested in doing one of the following two things: modelling their system of interest and trying out different behaviour rules. You model your system by dragging and dropping all the people and other actors into the initial condition and pressing play. If you have data from the real-world system, then you can use the simulation-based inference to learn interesting parameters of your system, such as the probability of some interaction or other things you are curious about. By inspecting the simulation, you can observe the dynamics that are at play in your system. And you can model alternative scenarios and observe how the dynamics of the system would change if, for example, one of the stalls had a sale or any other change was made. It is important to remember that not only you are modeling your system of interest this way, but many other researchers are modeling their systems of interest too. And they are all using the same agents to do so. The other thing you might want to do is try out different behaviour rules. Like any mathematical model, the happiness rule from earlier was just a guess. We guessed that someone's happiness might depend on their hunger, their spouse's happiness, and their country's average happiness. Any other happiness rule might just as well be true. Here, for example, we have a happiness rule that depends on someone's income and the number of close friends they have. Now, Tree of Knowledge has a very powerful way of automatically testing whether this new behaviour rule is better than the previous rule. The first step of this rigorous evaluation process is to fit the new rule by finding the best performing parameter values. Here a novel technique comes into play. We have to realise that the previous happiness rule was fit on many different datasets. The software automatically fits the new rule on most, if not all, the same datasets. It fits the happiness rule to the data from the happiness study. It also fits the rule to our purchasing decision data using simulation-based inference. And it fits it also to all the other datasets from all the other researchers. This is possible because all researchers used the same human agent with the same happiness and other attributes in their simulation models. Training parameters on all these different datasets simultaneously is very powerful. It not only provides a higher accuracy, it makes the rule also much more robust and immune to biases and other problems that exist in datasets. After automatically fitting the new happiness rule to all these datasets, the software automatically evaluates the fitted rule. This is done by checking if the new rule gives us more accurate simulations than the previous one did. From the individual accuracy scores, we can determine an overall accuracy. If this overall accuracy is better than for the previous rule, we keep the new rule. Just as a side note, it took physicists hundreds of years to evaluate the validity of the rules of mechanics in all these different scenarios. What took physicists hundreds of years, we can have Tree of Knowledge do for us automatically in a few hours. This might seem a little overpowered, but this power is necessary if we are to tackle the immense challenge of creating an exact theory of social systems and human behaviour. We have to remember that in the past, whenever people tried to come up with a set of rules for human behaviour, these rules turned out to make very wrong predictions. With Tree of Knowledge, it will be the same. The first set of rules we come up with will almost invariably be bad, which is to say that the resulting simulations will be jolly inaccurate. Even after fitting the model parameters, we might only achieve an overall accuracy of, say, 23%. Fortunately, it now is easy for us to change some of the behaviour rules and have the system evaluate them for us. The system will rerun all the models with the new rules and see how accurate the simulations now are. If the overall accuracy, here 32%, has gone up, we keep the new rules. By trying out different sets of rules like this, the accuracy will continue to increase, until we get to something like 92%. So, what we've just now done is learn the fundamental behaviour rules of humans. Just like the fundamental rules of mechanics were shown to accurately model hundreds of different mechanical systems, we have shown these rules to accurately model hundreds of different social systems. And just like the laws of physics that can be used to accurately model any new, previously unseen mechanical system, we can now use these fundamental rules of human behaviour to model any previously unseen social system. So, to summarise, by fitting and evaluating many behaviour rules for a fundamental human agent, we were able to find the fundamental rules of human behaviour. Just like in physics, these rules have been proven to work in hundreds of different scenarios. They are so versatile as to allow us to model any social system, and they give us decently accurate predictions. One last thing. Realistically, we will never achieve 100% accuracy, and even with fitting the rules, we might level out at a 92% accuracy. This software, however, uses a Bayesian framework that accounts for the uncertainty in predictions and always forecasts a probability distribution of outcomes. We can see that as our accuracy increases, the uncertainty around predictions decreases. So, despite not having 100% accurate predictions, we are at least aware of the exact uncertainty of every prediction. To summarize everything, by combining the proven and versatile fundamental model approach from physics with the accurate model fitting and evaluation approaches from statistics, we have obtained a model that should allow social scientists to create an exact science of human behaviour.